Unit 5, pages 10 through 16, System and Surroundings. Alright, system versus surroundings. The system is something of particular interest, such as a chemical reaction, and the surroundings is everything else in the universe except the system, so everything around the system. Examples: a pot of boiling water might be divided into this classification of system and surroundings. So the liquid that's actually boiling would be considered the system, and then everything around it would be considered the surroundings. A gas piston expanding against the atmosphere at constant pressure. In this case, the system does work on the surroundings. The surroundings are being pushed back. So the gas is the system, and because it's expanding, it's pushing on its surroundings, and so that is the work done as expansion on the surroundings. Notice that heat is being done on the system, or put into the system. Types of systems. The surroundings can interact with the system in many different ways. Two basic types of systems are used. There's an isolated system. Neither matter nor energy can flow between the system and surroundings, and a closed system. Energy can flow between the system and the surroundings. A chemical reaction can take place, but no atoms are gained or lost in the system. So here's a diagram of an isolated system where neither energy nor matter are able to get into the system. But a closed system is where you can have energy enter the system, but you can't have matter enter the system. This is an extremely important concept, the sign convention for energy flow. Heat or work gained by the system is going to be positive. Heat or work lost by the system is going to be negative. So notice in our diagram here that when the system gains heat, it's a positive change in heat. And notice that when work is done on the system, like if you were to take a balloon and compress it, then that would be work being done on a system, and so that's positive. And then when you have work being done on the surroundings by the system, such as if the system were expanding, it would be doing work on the surroundings. That's going to be negative work. And then if you have heat leave the system to the surroundings, that's going to be negative heat. Example 5.3. Look at the following process and determine the signs for heat and work at constant pressure. Don't forget that aluminum expands when it is heated. So notice here we have aluminum as a solid before and is still a solid afterwards. However, the temperature is changing. So what's happening is our original aluminum as a solid at 300 Kelvin versus its surroundings. So this is our system. And in order to go from 300 to 320 Kelvin, we have to add heat into the system. And so since heat is being added to the system, then we're going to put a positive sign for heat. But because the aluminum is expanding, then that means that it's actually pushing outwards or doing work on the surroundings, which is going to be a negative sign for work. Note, when considering the work, look for something moving against a force. The work is small in this case because the volume change is very small. Nevertheless, the sign is going to be negative for work. Example 5.4. Look at the following process and determine the signs for heat and work at constant pressure and temperature. So notice that we start out as a solid, CO2 solid, and it's going to turn into a gas. Well, what do you have to do to a solid to turn it into a gas? Well, heat is going to have to be added to it in order for the particles to move faster and expand and turn from solid to gas. So that means that heat is going to be positive in this case. Also, what is happening? Well, whenever we have a gas, it's going to cause this to expand against the surroundings, and so we are going to be expanding, which is work done on the surroundings, which means we have a negative sign for our work. Example 5.5. Calculate the expansion work when 1 mole of carbon dioxide sublimes at 77 Kelvin and constant pressure. So if you think back, we have work is equal to negative pressure times the delta V, which is change in volume, and the change in volume is equal to delta N RT over P. So if we were to substitute this equation in for the delta V, we would get an equation that looks like this. Work equals the negative P times delta nRT over P. Notice here our pressures will cancel with one another, and that gives us this equation. Work is equal to the negative change in moles times R times T. So work is equal to the negative change in moles is going to be the moles of product that are gases, which is 1 mole, minus the moles of reactants that are gases, which is 0 moles. Remember that solids and liquids are negligible. R is going to be the value 8.314 times the temperature, which in this case is 77 Kelvin. And so when we do this math, we're going to get work equals negative 640.2 joules. Here's your note card for this section. So first, define system versus surroundings. The system is something of particular interest, like a chemical reaction or a gas, liquid or solid. The surroundings is everything else besides the system. There are two types of system, isolated and closed, where isolated, no energy or matter can enter the system, whereas in closed, you can have energy enter but no matter. When you have phase changes, it's good to know that when you go from a solid to a liquid to a gas, heat has to be absorbed, while when you go backwards from a gas to liquid to solid, heat has to be released. And so that's exothermic and that's endothermic. Sign convention for energy flow. Remember, Q is going to be our symbol for heat and W is our symbol for work. So work and heat, if they both enter a system, then it's going to be positive work and positive heat. Endothermic is going to be considered positive heat. And then if the system is doing work on the surroundings, then work is being pushed outwards. And then if heat is being released, then you're going to have a negative sign for both of them. Usually, in chemistry, you're looking at more like heating a gas, where heat has to be absorbed, and then the gas expands against the surroundings. And so you have positive heat and negative work. Or if heat is released by the system, then it's going to contract, which means the surroundings are doing work on the system. Therefore, heat is negative and work would be positive in the case of cooling a gas.